Good morning, student. I welcome you in this special session on electrochemistry, particularly your course number CH203. And you are all the student of MSc second semester chemistry, and unit is 3. As you know that this is a very important unit, and it is related to electrochemistry. And if you have gone through your course content, you will see that one of the most important aspects of electrochemistry course is electrode interface, and particularly electrode kinetics. And you all know that one of the most important equation in electrochemistry, which has tremendous application in various fields of electrochemistry, starting from solar cell or battery or corrosion, everywhere. So what I am thinking that because it is a very broad subject, so I have divided my lecture on Butler Volmer equation into 2 parts. In part 1, the first half of this lecture, I will discuss the basics of Butler Volmer reactions. That means, because whenever you are talking about the Butler Volmer reaction, there are some important concepts. One is current density, another is the overpotential. So before going into details of the Butler Volmer equation, you must know what is the actual meaning of exchange current density, what is overpotential, what is the relationship between the exchange current density and overpotential, and then of course the other important things. So the first part is based on the fundamentals, and of course I'll discuss some of the genesis of the Butler Volmer equation. Fortunately, I have delivered Tafel equation, but Tafel equation is the part of the Butler Volmer equation. So I should have teach the Tafel equation after these Butler Volmer equations. As you know that whenever I start any topic, I always discuss with my student that what are the current literature or what are the good books available in our library for the electrochemistry. So for this today's lecture, I have referred one important textbook. You all know this textbook, that is called the Physical Chemistry by Atkins. I have also referred some of the research papers related to Butler Volmer equation, as well as my most favorite book, Bockris and Reddy, then Samuel Glaston's and other things. As you know that this is a very important equation, and title is the Butler Volmer equation in electrochemical theory: origins, value and practical application. Don't worry, I will not discuss the application today, because I think that I will cover today these 2 lectures, but I will not discuss the application of this Butler Volmer equations. And as you know that name itself is always a definition. So quite naturally it is a Butler Volmer. That means there are 2 scientists. They contributed. So therefore it is called as the Butler Volmer equation. And this is the diagram, photographs of great British scientist, physicist Butler, and he actually published, because both the scientists have done the work separately, because he is British scientist and Volmer is the German scientist. So now the general history is that in 1924, great scientist Butler, I'll show you the original research paper. He published a paper which relates, you think, 1924, no question of transition state theory, but that theory was developing that time. And so it is a relationship between some electrochemical reactions and activation energy. And of course, the role of electric potential. Because if we are talking about a electrochemical reaction or redox reaction, so it is also one type of chemical reactions. So yes, free energy or activation energy plays a very significant role. So he published that one. And the other scientist, Max Volmer, in the same time, between this 1924 and 1930, he is also working on the role of electrochemistry and some potential, overpotential and other things. Of course, with the other scientists. And honoring both the contribution, the present form, because they have done the work independently. Now we are talking about the whole equation is the Butler-Volmer equations. In one sentence, we are concerned about the electrochemical kinetics, or sometimes we call the electrode kinetics. Now, this is the research paper published in 1924. Thanks to the Google and internet, everything is available nowadays. Everything is available, of course. So you must know that this is the first paper published in a very good journal of Royal Society of the Chemistry, Transaction of the Faraday Society, 1923. Today is 2025. You see the things. The same Nernst equation and oxidation reduction, kinetic interpretation of the Nernst equation, and ultimately we are talking about the electrode reactions and thermodynamics and other things. Okay, and why I told you that sometimes in some literature it was considered as Erdős-Volmer equation. Because when in 1930 जब वोल्मर ने इस पेपर को पब्लिश किया था along with this scientist, and this is the original, but of course it is in German language, Z Physical Chemistry 1930. But basically it is also based on, you see, overpotential and electrode density. So that is the very short history of this theory. Now my first question, that if I ask you that define Butler-Volmer equation. In one sentence, you can talk that it is the first quantitative model for any electrochemical reactions. Particularly today's presentation, I will use one electron reduction system. Okay. Number two, that it is a relationship between current density, I will ask you the question, and overpotential. Third, if we are talking about any chemical reaction, because in first semester you have already studied the chemical kinetics. If I am taking out the simple chemical equilibrium, we know that time we need the chemical potential is the driving force. कोई भी reaction होने के लिए fugacity or that is there, and there is a activation energy, you all know. Now consider the same thing, that it is an electrode reaction. So here is also there is a activation energy. So what is the role of electric potential on that activation energy? तो कुल मिला के आप क्या बोल सकते हैं? तीन aspects. Number one, current density. Number two, overpotential. Number three, free energy of activation energy. But it is a very, very important equation because if you understand this equation, you can throw light on the current potential behavior of that reactions. अभी मैं समझाऊंगा क्या होता है. Number 2, that is a universal equation, because whenever you are talking about any redox reaction, there is a possibility of oxidation, there is a possibility of reduction. You all know oxidation कहाँ पे होता है, reduction कहाँ पे होता है. इलेक्ट्रॉन ट्रांसफ़र हो रहा है, तो उस इलेक्ट्रॉन ट्रांसफ़र के कारण पोटेंशियल एनर्जी चेंजेस होता है. तो हाउ दैट पोटेंशियल एनर्जी, दैट इलेक्ट्रिकल पोटेंशियल इज affects that energy of activation or the free energy of activation, like that. And it is very, very important because it can be used for most important application like battery, as I already told you, fuel cells and other things. So this is the simple introduction of that equation. Now you please go through that paper. He published the first paper in the year of 1924. उस समय ट्रांजिशन स्टेट थ्योरी हुआ था क्या, जो हेनरी आयरिंग, वाइन जोन्स, वो करीब करीब 1930 के आसपास हुआ था. What is the energy of activation and transition state theory? You all know. Different thermodynamic parameters can be determined. Then when they published, Eyring and Ledler, they published the research papers regarding this activation energy and the free energy of activation, entropy, enthalpy. In 1941, that Ledler and Eyring, when they published the application of theory of absolute reaction rate. अब आप एकदम सिंपल भाषा में मैं आपको समझा रहा हूँ. मतलब केमिकल रिएक्शंस के बारे में हम लोग जानते हैं, लेकिन अगर हम उसी थ्योरी को अगर हम इलेक्ट्रो रिएक्शन में अप्लाई कर दें, दैट इज बटलर वोल्मर इक्वेशन. तो व्हेन दे पब्लिश दिस पेपर इन 1939 फॉर द ओवर वोल्टेज, अब आपके मन में डाउट होना चाहिए कि व्हाट इज द डिफरेंस बिटवीन ओवर वोल्टेज एंड ओवर पोटेंशियल. इफ यू सी द ओल्ड लिटरेचर like that, you will see the over voltage. It is a synonym. अभी मैं समझाऊंगा कि what is over potential. So अब then same time आप देखिए, see the scientific development. Now in 1941, Butler, great scientist, he published the theory of hydrogen voltage, and using in recent papers Eyring, Glaston and Ledler have applied the transition state. अब आपको एकदम डेफिनेशन समझ में आ गया होगा कि अब बटलर वोल्मर इक्वेशन में हम लोग करंट डेंसिटी ओवर पोटेंशियल के साथ किसका रिलेशन करेंगे, फ्री एनर्जी एक्टिवेशन एनर्जी, एंड दैट इज आवर फाइनल रिजल्ट. सो नटसेल में ये बहुत ही सिंपल इक्वेशन है. अब मैं नाउ आई इन सेकेंड पार्ट आई विल डिराइव इट. अभी मैं डेरिवेशन इसमें नहीं कर रहा हूँ. नाउ जैसा कि आप जानते हैं कि वेन एवर आई टीच एनी थिंग, फर्स्ट आई मस्ट know what is the final equation of Butler Volmer. कैसा दिखता है, क्या है, without knowing anything. Like आपने देखा होंगे जब मैं आपको एक्टिवेशन एनर्जी पढ़ा था, मैंने आई फर्स्ट डिस्कस दी आर्नियस इक्वेशन, फिर मैं उससे कोलिजन बताता था, फिर कोलिजन से फिर मैं एक्टिवेटेड कॉम्प्लेक्स थ्योरी का बताता था कि नहीं, फिर हम डिराइव करते थे. तो अभी मान लो आपको कुछ नहीं मालूम, जस्ट आई आस्क यू दैट व्हाट इज दी general formula of Butler Volmer equation. There must be some confusion. Therefore, deliberately I have written here the reference of Atkins physical chemistry. Because जब आप घर में जाके different अच्छे books देखेंगे, तो there may be slight changes. In some places, transfer coefficient alpha they can be designated as beta. एक्सचेंज करंट डेंसिटी कई जगह में आई से दिखाएगा, एक्सचेंज करंट डेंसिटी कई जगह में जे से दिखा रहा. बट आई एम फॉलोइंग द बुक ऑफ एटकिंस एंड सी वेरी स्मॉल इक्वेशन एंड यू कैन वेरी इजीली रिमेंबर दिस थिंग. दैट अभी मैं समझाऊंगा कि अभी तो आप जस्ट पहले देखिए क्या है. देयर आर 3 टर्म्स. वन इज जे, आपको दिख रहा है स्मॉल जे. In some books, it is I से भी कह सकता है. It is related to exchange current density. मैं बताऊंगा what is exchange current density. And then again I just a common is J, but zero. Sometimes electric potential, if you apply electric potential, sometimes the rate of oxidation reaction, rate of reduction or cathodic reaction, anodic reaction is equal. So I have written is J0, and then there are three terms, exponential 1 minus alpha, negative positive में confuse मत होइए, minus alpha f and n eta. तो इसका मतलब है कि there is a relationship between the alpha is charge transfer coefficient. I will explain what is charge transfer coefficient. Eta is overpotential and it is the current density, and this is a short form of the Butler Volmer equation, and this is the another form. मैं आपको समझाऊंगा यहाँ पे आपको this f by RT can also be written as small f. फिर से मैं आपको बता रहा हूँ कि आई एम रेफरिंग दी किसी एक बुक को अगर आप फॉलो करेंगे तो आपको, बिकॉज यू आर ऑल स्टूडेंट, सेकेंड सेमेस्टर स्टूडेंट्स, सो फॉर एग्जामिनेशन पॉइंट ऑफ व्यू, yes, you must refer large number of research papers, large number of books, follow the teacher's instruction, लेकिन जब आप डेरिवेशन करेंगे तो किसी एक बुक को फॉलो करने की कोशिश करें, एंड ट्राई टू अंडरस्टैंड इट इज फिजिकल केमिस्ट्री. सो दिस इज दी थिंग्स. अब चूँकि ये फर्स्ट पार्ट में फंडामेंटल बात है तो मैं आई विल डिस्कस फर्स्ट दैट व्हाट इज कैथोड, व्हाट इज एनोड, व्हाट इज कैथोडिक करंट, what is anodic current, and what is exchange current density. So before I go into details of that anodic current and cathodic current, I must ask any student backside में, आप बोलोगे लड़का खड़ा हो, हाँ, फ्लो ऑफ इलेक्ट्रॉन बोल रहा है, ठीक है, फ्लो ऑफ चार्ज, फ्लो ऑफ चार्ज. What is the unit of current? Ampere. And current, if I am talking about the current density, flow of current through a material, through a electrode, or sometimes electrode donates a electron, sometimes electrode receives an electron. So you are right, flow of currents and other things. Now see, I am using as explicit, I am using, today I am using a very simple type of reaction. Again, why I am using the simple oxidation, loss of electron, gain of electron, you all know these things. And if I talk about a cell, so there is a electrode, and you know that you are right that there is a flow of charge or electron, whatever you are saying, and naturally due to this migration of electrons, a current is developed. And if it is a, you all know that in anode there is always oxidation. So that current is called the anodic current. And if it is a anodic current, so naturally the current density of or anodic current is greater than the cathodic current. So that what dominates, that oxidation process is dominates. And on contrary, if that cathodic current is greater than the anodic current, then what happens? That cathodic reactions, that means the reduction process is dominates. So whenever you derive any Butler-Volmer reaction, and the difference between this cathodic current or anodic current is equal to exchange current density. Now question arises, in some books you will find that if I write the exchange current density is equal to J0 suppose, or Ji equal to Ja minus J anodic current minus cathodic current. इसका मतलब हो रहा है हमने जो एनोडिक रिएक्शन को प्रीफर कर रहे हैं, डोमिनेट कर रहे हैं. इट डजंट मीन कि मैं एक्सचेंज करंट डेंसिटी को कैथोडिक करंट माइनस एनोडिक करंट भी हम लिख सकते हैं. यू फॉलो माई पॉइंट. तो जब आप अलग अलग बुक्स देखेंगे तो आपको कन्फ्यूजन होता है, सर आपने तो ऐसा लिखा है, JA minus JC is equal to exchange current density. क्योंकि मैं ऐसा दिखाना चाहूँगा कि मेरे केस में, although I am taking a simple example, oxidation, I will show you a simple single electron transfer reaction मैं दिखा रहा हूँ, लेकिन कोई भी electrochemical reaction में दूसरा भी हो सकता है, but for simplicity I am using a single electron transfer reaction and I am just showing a reduction type of the reaction. So it is up to you, आप कैसे लिखेंगे. देखिए अब मैं why I am just comparing you the simple chemical reaction. A is converted into B, simple chemical reactions, and you all know that at equilibrium rate of forward reaction is equal to rate of backward reaction, same thing. And what is the driving force? आप लोग बोलते हैं chemical potential. आप उसी तरह से सोच लीजिए कि I am now talking about the one electrochemical reactions, same types of the reaction. A is a electrode, electron, so it is a reduction type of the reactions. So A, if I write is the oxidized species, I can write here also OX plus 1 electron, and then this is the reduction. Okay. So A obtained 1 electron from the electrode and becomes reduced to species B, and while B release 1 electron to the electrode. But if it is electrode reaction, bear in mind, in addition to chemical potential, one of the driving force is electrical potential. So whatever I want to calculate regarding the electrode density, अभी मैं ओवर पोटेंशियल का बात में नहीं आया हूँ, ओवर पोटेंशियल, एक्स्ट्रा वोल्टेज, थर्मोडाइनमिक पैरामीटर्स है जब इक्विलिब्रियम हो गए हैं. समटाइम्स सम एक्स्ट्रा वोल्टेज इज नीडेड टू ड्राइव द एनोडिक रिएक्शन टू फैराडिक रिएक्शन, मतलब वो इलेक्ट्रॉन ट्रांसफर के लिए. अभी मैं एग्जांपल दूंगा. इफ यू आपने एक बनाइए, एक हाइड्रोजन इलेक्ट्रोड लीजिए, उसके साथ एक कॉपर का निकल का लीजिए. आप तो जानते हैं हाइड्रोजन का स्टैंडर्ड इलेक्ट्रोड पोटेंशियल इज 0, तो क्या रिलीज करेगा? नहीं, एक्स्ट्रा पोटेंशियल applied potential will be required. So the difference between the thermodynamic potential और equilibrium potential minus जो applied अपने potential, वो दोनों का जो difference है, that is the over potential. Agreed? So and again you just, I am not going into details of that. Mu 0 is equal to, just you think thermodynamics, mu is equal to mu 0 plus RT natural log of activities. अगर आप फर्स्ट सेमेस्टर में ठीक से इलेक्ट्रोकेमिस्ट्री को पढ़े होंगे तो देन, पहले मैं इलेक्ट्रोकेमिस्ट्री पढ़ा था तो मैं बहुत दिन से नहीं पढ़ा रहा हूँ. फॉर लास्ट ईयर आई हैव सीन दैट टैफेल, कोई किसी ने नहीं पढ़ा, फिर मैं टैफेल को आपके साथ डिस्कस किया. एंड जैसा इन टैफेल में आपने देखा कि आई डिस्कस दैट टाइम वन आडिल, डॉक्टर आडिल वॉज हियर एज ए गेस्ट लेक्चरर, ही डिलीवर्ड दी बटलर वोल्मर. दिस ईयर आई हैव सीन दैट यू हैव नॉट, इसको आपने नहीं पढ़ा, तो मैं सोचा कि एक बार पुराना बात में आ जाऊं, फिर मैं स्टार्ट करूं. सो डोंट वरी अबाउट दिस थिंग, डोंट राइट एवरीथिंग दैट म्यू इज इक्वल टू म्यू 0 प्लस, बट हियर Z is the charge actually. F, you know Faraday, you all know what is Faraday. What does it mean of the Faraday constant? आप जानते हैं. The one, that's what. And phi is the potential. So now it is clear what is actually cathodic current and what is anodic current. Now the second part. Just a minute, ऑफिस का काम भी करना पड़ता है. Now if you define, if I ask you define the current density is the amount, क्योंकि in sometimes in examination before first point, because it is in your prospectus, what is current density and over potential. So there must be clear-cut definition of the current density is the amount of electric current passing through a given area of conductors. So therefore, generally in current we write ampere, but it is a electrode. So the unit of current density is ampere meter square, and it determines the rate of flow of electron, which is very, very important. Because if you know if the current density is high, or The higher current density means faster the deposition rate. So it is very important. Now how do I calculate the exchange current density? Now you please check it very carefully that in this particular derivation, in the second part, there should be no confusion. I am using deliberately the net current density is equal to J is equal to JA minus JC, small j, j. You can also write small I or IC, because here I am using the shift of potential in anodic directions. That means anodic current density is greater than the cathodic current density. Alternatively, आप JC minus JA भी लिख सकते हैं. In that case, shift of potential in cathodic direction. तो इसमें मतलब ये आपका कोई कंफ्यूजन नहीं होना चाहिए कि कुछ बुक में सर ऐसा लिखा हुआ है, कुछ बुक में ऐसा लिखा हुआ है. और at equilibrium, you know that JA is equal to JC. So net current density is equal to JA minus JC. So due to the, if it is a anodic current density, due to the oxidation, increase with increasing potential. And the cathodic current is balanced by the anodic current. So that time we generally write, you have already seen that our first equation, we have written that J0 is equal, J is equal to J0. J, what is explained, मैं समझाऊंगा कि what is actual J0 जब हम पूरा derivation कर लेंगे. And the value of Ji and value of Jc. It is clear? अब आ जाइए second part, the over potential. इसको भी अच्छे से समझ लीजिए. Yes, in old books, if you see the Glaston, more electrochemistry by Glaston, yesterday I have just, when I have gone through the, मैंने देखा उसमें over potential के जगह में over voltage लिखा हुआ है, hydrogen over voltage. There are different types of over voltage, but here, because we are concerned about the chemical reactions and transition state theory, activated complex, because there are various types of overpotential, concentration overpotential, activation overpotential. Bear in mind, here we are using the activation overpotential, okay? And this is the overpotential, extra voltage. Because normally there is a thermodynamic equilibrium, you know. But we have to apply some extra voltage for any electrode kinetics, electrochemical reactions. So that drives the Faradic current, means electron transfer. Okay. So in simple sentence, again आप फिर confuse हो जाएंगे that सर हमारे किताब में तो ऐसा लिखा हुआ है. Simple system is that over potential is equal to E applied, that is extra voltage, and thermodynamic equilibrium is E. Or in somewhere, if I just consider that E applied is E dash, E applied is E dash minus equilibrium is E normal, so that is also eta. Or in some cases, that E dash, that means E applied can also be, because that is also important, applied voltage, applied potential. So eta also you can write that this is applied delta phi, and that is the equilibrium. That is the difference. फिर मैं आप बार-बार आपको बोल रहा हूँ extra voltage. The potential difference at the interface, current flow to that electrode. And the relation, इन दोनों का जो relation है वही हमारा बटलर वोल्मर इक्वेशन है. अब एक आध एग्जाम्पल मैं देके आपको समझाता हूँ. Suppose why this over potential is needed? A short answer type of the question. Why we are interested in this? In normal cases, there is a thermodynamic equilibrium. So what is the need of such type of thing? It is a driving force. So therefore, it is very, very essential that for any electrochemical setup, any battery, if I want to use any solar cell or even sensor, we have to apply this thing because this is normal case E equilibrium. But हमको लगेगा ही लगेगा. In a real electrochemical system, the redox reaction do not proceed, and sometimes what happened that electron transfer rate is very slow, sluggish. Then you know that there is a mass transfer, maybe diffusion होगा, migration होगा, concentration होगा, potential होंगे, electrode surface properties. Because over potential, if I ask you that what are the different factors, there are many factors. Temperature is one of the factors, solvent is one of the factors, the material of the electrode is one of the factors. ऐसे बहुत सारे factors हैं. इसलिए ये तो extra driving force is needed to overcome these barriers. तो इसलिए over potential को तो देखना ही पड़ेगा. And I am giving one example that hydrogen evolution system. Okay, so you want to generate hydrogen, and you know that is a very burning topic. आप सुनते हैं ग्रीन हाइड्रोजन के बारे में, हाइड्रोजन का आजकल गाड़ी भी हाइड्रोजन से चलाने का बात हो रहा है. तो भारत सरकार का बहुत बड़ा प्रोग्राम है हाइड्रोजन जनरेशन. So everybody is working on the hydrogen generation, and you know that in standard potential of hydrogen is 0 volt. But in practice, if I take one platinum, if I take some nickel, so I need extra voltage, 0.3 to 0.5 volt like that. So that is called the overpotential. तो अब पहला भाग में मैं बहुत संक्षेप में आपको समझाया. एक सिंपल रिएक्शन में लिया, रिडॉक्स रिएक्शन. मैंने आपको समझाया कि कैथोडिक करंट क्या होता है, एनोडिक करंट क्या होता है. फिर मैंने आपको समझाया कि अब हम उस रिलेशन में आएंगे कि कैथोडिक करंट, एनोडिक करंट एंड रिलेशनशिप बिटवीन दी ओवर पोटेंशियल. अब लास्ट पार्ट में आ जा रहा हूँ, फर्स्ट पार्ट का लास्ट पार्ट. आई ऑल्सो नीड ए वाटर. 2 लगातार लेक्चर करना है. नाउ it is a very important part. We understand the current density, clear. We understand the exchange current density. We understand the overpotential. Now apply this overpotential in any electrode type of the reactions. First आप भूल जाओ, simple A is converted into B. फिर मैं MSc previous में आ जा रहा हूँ. A is converted into B. So rate is equal to some K A. ऐसे ही हो रहा है ना. And you all know that K is equal to KB T H exponential minus delta G by RT. Now in place of simple rate constant, I am using oxidation and reduction. So one forward, one backward. एक कैथोडिक रिएक्शन, एक एनोडिक रिएक्शन. वही हुआ ना. अब मान लो what is the rate of oxidation of reduction? So we can write K, because अब इधर का हम देख रहे हैं. देखिए, here the substrate is reduced. So therefore I have written here K reduced. And this side, cathodic current, substance is oxidized species, oxidant. So any doubt about this thing? Ab we have to apply this rate constant in terms of cathodic current. And fortunately there is a formula that if I want to calculate the in place of rate, मान लो मैं यहाँ पे लिख रहा हूँ IC, sorry, we are using JC and JA. आप अच्छे से समझ जाओ. हम रेट ऑफ रिएक्शन की जगह में हम यहाँ पे एथोडिक करंट का मतलब ये होता है ना, रेट ऑफ ऑक्सीडेशन, रेट ऑफ रिडक्शन, रेट ऑफ फ्लो ऑफ इलेक्ट्रॉन्स एंड अदर थिंग्स. बट हियर वी आर playing with the Faraday, number of electron change, potential and other things. So in place of rate, whatever our product flux or whatever our rate, it must be multiplied with Faraday, F, and number of electron change. But because here we are using single electron transfer reaction where n is equal to 1, इसलिए मैं n को नहीं लिख रहा हूँ. और अब हम इसके इस रेट कांस्टेंट के साथ उसको रिलेट करेंगे तो हमारा बटलर वोल्मर इक्वेशन आ जाएगा. कैसे? अगेन आई एम सीइंग, देखिए ये आई एम टेकिंग फ्रॉम अनदर लिटरेचर, तो यहाँ पे आई दिखा रहा है इसलिए आप कंफ्यूज हो रहा है. आप यहाँ पे फिर करो जे स्मॉल जे इज इक्वल टू जे ऑफ ए माइनस जे ऑफ सी, and in place of j I can write n f. ये जो मैंने फैराडे बताया ये रिडक्टेंट है. सो व्हाट इज दिस? इज एनोडिक करंट डेंसिटी और कैथोडिक करंट डेंसिटी n f. ऑफकोर्स किया मैं के लिखने भूल गया, के तो रह गई. एनोडिक करंट के सी ऑक्सीडेंट. एन को मैं इसलिए नहीं लिख रहा हूं बिकॉज एन इज इक्वल टू 1 हियर. सो जस्ट आपका समराइज आप क्या करो, अगर आप सब कुछ भूल गए आप लिखो जे आई वॉट एवर इट इज इक्वल टू एन एफ के एंड ऑक्सीडेशन स्पीसीज और रिडक्शन जो स्पीसीज यहाँ पे है, एंड सब्सटीट्यूट द वैल्यू ऑफ के का क्या वैल्यू है? के का वैल्यू है के बी टी एच एक्सपोनेंशियल माइनस डेल्टा जी एक्टिवेटेड डिवाइडेड बाय आर टी. यू फॉलो माई पॉइंट और नॉट? Relationship between current density and rate constant. Just you forget rate is equal to K and reactant हम लोग ऐसे लिखते हैं. यहाँ पे हम क्या लिख रहे हैं? केवल हम एक प्रोडक्ट फ्लास्क मतलब उसमें फैराडे को जोड़ रहे हैं. सो J इज इक्वल टू फैराडे, K ऑक्सीडाइज स्पीसीज और रिड्यूस स्पीसीज. एन हम इसलिए नहीं लिख रहे हैं बिकॉज हियर इट इज ए सिंगल इलेक्ट्रॉन ट्रांसफर, इसलिए हम एन इज इक्वल टू 1. अगर आपका दूसरे टाइप का 2 इलेक्ट्रॉन ट्रांसफर, 3 इलेक्ट्रॉन ट्रांसफर, देन ऑफकोर्स एन प्ले ए वेरी सिग्निफिकेंट रोल. ओके, सो नाउ अगेन आई हैव जस्ट रिटन सेम थिंग बट अगेन सेम थिंग यू सी. मैं बार बार इसलिए लिख रहा हूँ ताकि अलग अलग लिटरेचर से हम लोग जब हम लेक्चर तैयार करते हैं तो आई फॉलो डिफरेंट टाइप्स ऑफ बुक, रिसर्च पेपर्स. बट अगेन आई एम सेइंग दैट वी आर जनरली बेसिकली बेस्ड ऑन द फिजिकल केमिस्ट्री बाय एटकिंस, है ना, इसलिए हम एटकिंस को ज़्यादा फॉलो कर रहे हैं. फिर वही देखिए, फिर से मैं बार बार आपको याद कराने के लिए, इतना सिंपल रिएक्शन है बट इफ़ यू आर नॉट सीरियस you are not able to understand the things because it's a teaching, therefore I am using so many things. But when you derive it, you just write directly. You can write this cathodic current is just forget about the F, forget about the N. Just याद करिए rate is equal to rate is directly proportional to some reactant concentration, and if you just remove that proportion तो एक constant आएगा. तो सेम वही है, रेट कांस्टेंट सेम वही है, केवल एक एफ इसमें जुड़ा है. एंड नाउ द नेट करंट डेंसिटी वेयर एनोडिक करंट इज डोमिनेटिंग, एनोडिक करंट इज ग्रेटर देन कैथोडिक करंट. सो देयरफॉर आई हैव रिटन हियर जे ए माइनस जे सी, एंड आई जस्ट रिटन द कंप्लीट वैल्यू ऑफ एफ. ये थोड़ा सा टाइपिंग ठीक से नहीं हुआ, एफ देन के ए एनोडिक करंट रिडक्ट माइनस अगेन एफ एफ कॉमा के सी एंड ऑक्सीजन। इतना इजी है, सोचिए। दिस इज इक्वल टू एक्सचेंज करंट डेंसिटी। और उसके बाद ईटा वाला भी हमने आपको थोड़ी देर पहले आपको दिखाया था ना कि ये अप्लाइड माइनस ई इक्विलिब्रियम, चाहे आप डेल्टा फाई के रूप में करिए। अब इसके साथ आपका रिलेशनशिप क्या करना है, दैट इज द बटलर वोल्मर इक्वेशन। सो थैंक यू वेरी मच। दिस is over the part 1. Let me summarize just one thing, that now in the second part, it is a very short part. In first part, as per your prospectus, first part is that you must know what is current density, what is overpotential, the relationship between the current density and overpotential. I have already discussed. And second, I have already discussed the relationship between the rate constant and cathodic current and anodic current. Now in second part, I will derive everything. That means I will do nothing, because again and again I am saying in the second part what we have seen that J, if I write J is equal to F is common, N I have not written because single electron transfer or N, and K may be cathode or anode, I have not written anything. Species S, because I have not written canodic current on cathode. So in Butler Volmer equation, what I will do substitute the value of K using transition state theory, because we are using kinetics. And then in transition state theory there is a term free energy of, or in some books they have written the gives energy of activation. Because I am also not convincing about the free energy नाम का कुछ नहीं होता है, लेकिन हम लोग पढ़ रहे हैं free energy, free energy, free energy. It is basically gives energy of activation. And then we will see the relationship between the delta G, you all know, minus N E F, याद आ रहा है? ये सब है। फिर हम ईटा N नंबर ऑफ इलेक्ट्रॉन्स है, ये G C का देखेंगे, फिर ट्रांसमिशन कोफिशिएंट देखेंगे। अब आपको समझ में आ गया होगा। अब हम सेकेंड पार्ट में हम बटलर वोल्मर इक्वेशन को डेरिवेशन करेंगे। आई विल नॉट रिपीट द फर्स्ट पार्ट because I have already solved this part. I have to just first apply the value of K in this equation. I will get the delta G. Then that is very important, is delta G के साथ ओवर पोटेंशियल का क्या रिलेशन है, चार्ज ट्रांसफर कोफिशिएंट का क्या रिलेशन है, एंड देन आई विल गेट ए कंप्लीट इक्वेशन ऑफ द बटलर वोल्मर इक्वेशन. थैंक यू.